So section 3.2, we're going to spend some time specifically looking at an exponential function to look for patterns in its derivative, so we can look for some shortcuts. So by definition, what we mean by an exponential function is any function where your input, or in other words, your variable, is the exponent. So exponent for exponential. So for example, we could mean things like 2 to the x, 3 to the x, 4 to the x, e to the x, so on and so forth. So to get it started, we're going to look at a real-life application of this. So I've just inserted the graph of 2 to the x, and we're going to pretend that this function, we're going to use t for time, 2 to the t will represent the population mass of just some animal that I made up at any given time t. And as I'm noting here, I'm choosing to use population mass because it better describes the continuity of the function that I've listed below. If we just think about like total number of people in the population, we'd expect some jumps, right? Because we know there can be one person in the population, or there are 2 or 3. The kind of difference between 1 and 2 people doesn't make sense, or creatures, if we count whole number of creatures. But if we think about their mass, then it brings some light to that decimal or the continuity between them. As they're growing, another person per se, they're growing in size. So eventually they'll have a full creature, but until then they're just adding to the mass of the population. So let's just start to take a basic look at this. We're just reminding ourselves that our function is an exponential function. We're kind of looking for the derivative, right? So the derivative of our function, what we know, is going to be some sort of change in mass given a change in time. So let's just very broadly kind of look at some changes here. So let's just look at this one day. So from day 1 to day 2. How did the population change? Well, it started with 2 creatures on day 1. At the beginning of day 2, there's 4 creatures, so that change was 2 total creatures. If we look at day, let's just do 3 to 4, for instance. So on day 3, it starts with 8 creatures, and by the beginning of day 4, there are 16. So in one day, it has increased 8 total creatures. One more time, let's just look at the difference between day 4 and 5. So it starts on day 4 with 16 creatures, and then on day 5, we now have 32. So again, we will see that's an increase of 16. What's important to notice here, though, is that the rate of change was actually the same value that it started the day on. So like here, it started at 2, so we know 2 is the same thing as 2 to the first power. On day 3, it started at 8, and it grew by 8, so we get some idea of 2 to the third. Here, on day 4, it started with 16 people, and then the change was 16 people. So we're seeing that the change was, again, 2 to the fourth. So right away, there seems some very basic connection with the rate of change of this exponential function being related to itself. Like I said before, on day 1, which was 2 to the first power, that's what we saw as change. On the third day, 2 to the third power, that's what we saw as change. So it's really, really, really intuitive that exponential function is related to its own derivative. However, this is not correct. This is too simplistic. It's on the right track, and I really am just showing this right now just to really enforce that there is clearly a relationship between the original function and its derivative. Now, it's not just itself, which we'll see further, but the idea is there's some sort of relationship between itself and its derivative, and then it'll make more sense in the actual formula. But the problem that we just did when we estimated the days there is we used a huge chunk of time. We used an entire day. But the true essence of a derivative is that we're supposed to be getting smaller and smaller and smaller amounts of time. And if we start thinking about time, a day is a huge amount of time. So we'd want to start looking at smaller and smaller values, like maybe like 1/10 of a day, or 100th of a day, or maybe even 1,000th of a day, 1,000,000th of a day, so on and so forth. We want to take our rate of change, our change in time, and make it smaller and smaller and smaller to actually get to the definition of a derivative. So with that, if we know that we have to make our change smaller and smaller and smaller, this is going to be our definition of the limit definition of the derivative. So what I've done here is I'm just going to simply put in the limit definition of the derivative. So in other words, the derivative of our function will model the change in mass over the change in time. So it's our original function. So here, again, I'm using d of t to represent that the time that we're measuring as change is getting smaller and smaller and smaller. So we take the original function plus that tiny measure of change and subtract away the original function, divide it by that total measure of change. Now, I've chosen to leave d of t there just to emphasize the change in time, meaning we want that time between the populations to get smaller and smaller and smaller. I am at this point going to transition over to our h notation, which we are a little more familiar to seeing in class. So what we have first of all is I started by just applying the limit definition using h instead of d of t, so that's the only change. So here, what I'm saying, once I have the limit definition, we know by the properties of exponents that if we have two bases that are the same and they're being multiplied, we could simply just add their exponents. So I'm actually going to do that in reverse. I actually added their exponents here, so I broke that down into the original two bases that must have been added together. From there, then what we can obviously see is that both terms on top, so this 2t times 2 to the h, and then this 2t, all have a common factor of 2t, which I have factored out and put in front of the function. Now continuing, what's important to see is that 2 to the t, we know that's just going to be a constant, right? When we are taking the derivative of a point in time, we know that t will have some sort of value, whatever that may be. So if we, if let's say t was 1, well, 2 to the 1, that's just a constant value. If t was 0.0001, well, that's again 2.0 to the 0.001, which is again just a constant. So what we're looking for here is that we know that 2 to the t will just be a constant. And the reason that's important then is obviously what we're going to do is we're going to apply that constant rule of the derivative and the limit here. So we can pull out that constant and put it in front of the limit. And what I want us to see is that, again, we're looking for the derivative of our function. So the derivative right here is what we're looking for. So we took that 2t and we pulled it out and we have the remaining limit. Now, just for simplicity, what we can see is that the derivative, and I'm looking just right here, the derivative, the definition of the derivative is going to be some sort of multiple, whatever this value actually is right here. Whatever this thing is, let's just call it k for right now. So whatever that limit will approach as h gets 0, let's just call that k. So super important thing that I've written on my notes here is that we can see, and again I've tried to identify it as super important, the derivative of our exponential function is somehow related to the original exponential function. In fact, it's proportional to that original function. It's not exactly 2t, but it's 2t times some sort of multiplier that I am calling right now k. Now just again to see that notation, I'm going to replace 2 to the power of t just as our original function, and this is what we're trying to say as super important. So our derivative right here, the derivative of our original function is the original function times some sort of constant called k. In other words, they are proportional to each other. Now just as a note, if that k value was 1, we can see here if this value was 1, then the derivative of an exponential function would be itself times that 1. Now that's going to be a super special case that we're actually going to look at last. But first we're going to investigate, well, if what we said here was that the derivative of an exponential function is proportional to itself, well, we obviously know what the exponential function is. How are we supposed to find that value of proportionality per se? How are we supposed to find that k? So the question becomes then, well, how do we find that k value? And just to begin with, I want to just look graphically, or excuse me, as a table at it so we can kind of just see the pattern. It's a little harder to do algebraically, so right now we'll just kind of do it, like I said, with the table. So what I have prepared in the table, I've provided an extra column that I've crossed out in case you have that on your notes. But we have two things we're looking at here. So this is what we're kind of looking for. This is our derivative function. We're trying to find that k value. And it's reminding you of what that k value was from the last slide. So it's the limit as h approaches 0 of 2 to the h minus 1 over h. So what I have here in our table is first I have h. So we can see that I'm making those values very small on the positive and the negative side. And then next that I've graphed 2h minus 1 over h. Now what we should look at is we can see here these negative values are getting smaller and smaller and smaller and smaller. So what we should see is that our k value, right, so what we've called k, is getting closer and closer and closer to this number. If we look at the other side, meaning if we look at positive values, so like these positive values are getting smaller and smaller and smaller and smaller, so we're getting closer and closer to 0. We also see that it approaches this number 0.693. So we can kind of see is that k is approximately 0.693. And to all our favorite math people out there, that's not just any random number. And I wouldn't necessarily expect you to recognize that as a decimal. But that's why you're here watching this video. I think it'd be interesting for you right now to go to your calculator and type in the natural log of 2. And after you do so, you will see that that will, on your calculator, be approximated to like 0.0693, so on and so forth. So what I'm saying here is k, really, if we evaluated that limit, k would equal the natural log of 2, which shouldn't be anything outrageous. We know that our original function, m of t, was really just 2 to the t, right? So I am trying to be very explicit now that we can see that the base of our exponential function is the input into our logarithm for our k value. Therefore, that brings us to our definition of how to find the derivative of an exponential function. We see that the derivative of an exponential function is, of course, proportional to itself. So in other words, I take the original function and multiply it by some measure of proportionality, some value of k, and now we're explicitly defining that k value to be the natural log of the base of your function. So we had talked about before, and what we're just seeing now is we know that if we have some function, f of x, which is an exponential function, we know the derivative of that exponential function is the original function times some sort of measure of proportionality, which is directly related to the base of the function. But in other words, there could be a time where this thing here was just 1, in which case the derivative would be the original function times itself, because times 1. So our question is then, like, when is that going to happen? When would this a and this a jive so that the natural log of a is just 1? So first I'm going to write that in symbols, right? So this was our limit definition of the derivative. Just like we did before, we're using the h notation here. We've factored out the common a to the x on both and left that out as a multiplier, so we've seen this before. And as we said, we want that k value here, this proportionality thing over here, that limit, which we're calling k just for shorthand. If we could find that k to be 1, then we know that the derivative would be itself. So in other words, just formalizing that, we want the k term, which was just our limit as h went to 0 of our k term, we want that to be 1. So in other words, what I'm now saying is we would evaluate that limit at some point. So if we found the small enough k value, in other words, if we did this limit, we want this to be our final outcome. We want this value to approach 1 as our h values become smaller and smaller and smaller. So in other words, after we apply this limit, we want this to be our answer. So we just do a little manipulation. We multiply both sides by h, and then we add 1. So after multiplying by h on both sides and then adding 1 to both sides, we should currently be here. Now to get to the last step, a to the h should equal h plus 1. Just like we can do with other exponents, we can raise both sides of the equation to a power. So I'm selectively going to choose to raise both sides of this equation to the power of 1 over h. So now we're simply just using the properties of exponents. So on the left side, if I had a to the h all raised to the 1 over h power, we know that with a power to power, we're supposed to multiply those exponents. So h times 1 over h just becomes 1. And then I've just left the left side unsimplified because I don't know what 1 plus h is to the 1 over h power. So what we're saying here is essentially, if we get our k value to be 1, that means that the a value itself needs to be approximated by 1 plus h to the power of 1 over h. Well, how the heck are we supposed to find out what 1 plus h is to the power of the 1 over h? That again is kind of hard to do. So I just want to look at it as a table so we can see the pattern and we won't algebraically prove it. But how are we supposed to find out what that a value is? Because if we can find that a value, then it make k1, and we have an exponential function that is its own derivative. So similar before, I've just prepared a table for you. So what I have here is h values. And we can see that those h values are starting positively and getting really, really, really close to 0. So smaller and smaller and smaller. So we should see the pattern in those outputs here. So that's in our second column. So our outputs are that function there. So that's the value of a. So we can actually see that it's getting closer to this 2.7183. We can see that again and again. And then what I did was just make sure that limit exists from both sides per se, just kind of see what is h approaching as it gets really, really, really small. So from the negatives, I've shown a little bit less, but we can again see that it's approaching that 2.7183. Now, just kind of foreshadowing before, we noticed that an exponential function was proportional to its base using the natural logarithm. If you're not already recognizing that number, at this moment, I would encourage you to go to your calculator and type in e, and it approximates it to 2.718. And that brings up two really huge things. What we were looking for before is we said that we know we have some exponential function, a to the x will be some multiple of its base, and again we called this thing here k. So we said if a was equal to this number here, which I'm now going to say is e, well then we would know that the derivative would just be itself times 1. So we found that special e value that would make the derivative itself. We've also just discovered something else super quick here. We noticed that if we took this limit right here, which I'm circling up here again in green, we can then conclude this because we just kind of saw this, so it's a nice little consequence. So this is our special derivative for e to the x. This is a special case of the exponential functions, the derivative of the exponential functions. Because again, we always know this to be true, that a derivative of an exponential function is equal to itself times some value of proportionality, which we discovered to be the natural log of the base. And we know that the natural log of e is just 1. So it's actually really, 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 really super important to see that e to the x is its own derivative. If you're not already on the e train, if you don't love the value e, then you need to spend some time falling in love with it because it's great. And one of the reasons we see here is its own derivative. Now, once we actually have the ability to prove that the derivative of e to the x is itself, we use some special limit there to find that. Then we can actually use that limit to prove the original rule that we found at the beginning. We just kind of did that using a table and not very accurately, but now that we kind of know this, we'd be able to prove it algebraically. I just took this from your textbook. They do a really great proof of it. And I think we should at least give it a little screen time per se. So you can see that first they start with that limit definition of the derivative like we did, and we understand that the derivative of an exponential function is going to be some sort of multiple, some sort of proportional to its original function. And you can see then, with a little fancy algebra, like rather than writing a, they take some time to rewrite a as e to the natural log of a, and all that good stuff. But you then see that they'll need to utilize what we just saw here, that we know that if our base was e, then that limit would go to 1. And once we have that, we can continue with the rest of the proof, which I leave to you. So at this point, you are done with your content. So just take a moment to check in. You should be responsible for two things right now. You should know the general rule for finding the derivative of an exponential function is always going to be some sort of proportional relationship to the original function, and that value of proportionality is the natural log of the base. Second of all, then we apply it more specifically, and we'd say, well, there's a special case. If the base was e, then the derivative of e to the x is just itself, because the natural log of e would be 1. Let's see a few examples in action, so just some quick applications of those rules just to get you started. So like for instance, we're supposed to find the derivative of this problem. So this is clearly an exponential function because the base is a number and our exponent t is actually the exponent, and so our variable is an exponent. So here we're just going to apply the exponential rule. So we know that the derivative of an exponential function is going to be the natural log of the base times the original function. That is the exact form. I'd leave it like that. If you really wanted to approximate it though, we would know that the natural log of 3.5 is like 1.25 times 3.5 to the t. Moving on from number 2, they want us to obviously see that we now have a base of e, but there's also a 2 in front of it. And now that 2 is just a constant multiplier. So as we know from the last section when we're calculating the derivative, so we know that the derivative, we could just pull that 2 out as a constant multiplier. So we'll pull the 2 out. Now the derivative without the 2 is just e to the w, and that is our special case e. If the base is e, the derivative of e to the w is just itself. So we will see that the derivative here is obviously just itself. Number 3 down here, just asking us again to apply a few more rules that we're already learning in context of what we just learned. So we have a sum function here. So if we wanted to find the derivative, that means we could just find the derivative of the first part of the function and then add it to the derivative of the second part of the function. Now the first part of the derivative is just a power rule, so that 2 would slide down. And again, this is an important differentiation. Here we can see that our exponent is a 2, so meaning our variable is the base. This is not an exponential function. This is just a quadratic, so we're just going to use the power rule. So that becomes 10t to the first. Moving on over here, we can see that this actually is an exponential function because our variable is the exponent. So the derivative of 4e to the t, similar, we could pull out that 4, and then the derivative of e to the t is just itself. So we'd again just add those two together. We're going to have our application of the sum rule here, so we could just find the derivative separately. So we could find the derivative of this term, so 12e to the x, and we could just simply add it to the derivative of the second term, which is the derivative of 11 to the x. So here, again, we can pull out that constant multiplier and then find the derivative of what's left, and we know the derivative of e to the x is just e to the x. And then we would add the derivative of the second term, and this is just the direct application of our exponential rule because our variable is the exponent, so we take the natural log of the base and multiply it by the original function. Number 5 now, again, we'll see that we will apply the sum rule again, so we would be able to find the derivative in respects to t of that first term, and we'd be able to add the derivative in respects to t of that second term. Now the first term, again, we have that constant that we can pull out in front and then calculate the derivative of what's left. We know the derivative of e to the t is itself. We would then add the derivative we get over here, and this is just a power rule because, again, our variable is not the exponent, it's the base. So this is just quadratic, so it's a power rule. So we drop that down, multiply it, so it'd be 2 pi times t. Number 6 is just kind of written weird, but if we let a equal the natural log of 2, then we're really just trying to find the derivative of a to the z. So we know that to find the derivative of an exponential, because z, our input here, is the actual exponent, so this would be the natural log of a times a to the z. So now we go back and substitute, well, what was a? It's just kind of written weird, it's just a natural log of 2. So the derivative here would be the natural log of the natural log of 2 times the natural log of 2 to the power of t. Now example number 7 is just there. It looks more complicated. We just got to rewrite it so it kind of fits our purpose here. So I'm going to choose to kind of rewrite things as multipliers because we know that we can pull out multipliers, so on and so forth. So I'm going to rewrite this as 1/3 times 3 to the a plus a to the negative 1/2 times e. So if we were looking for our derivative of our function k, we see that it's the sum of two different things. We kind of find them independently and then just simply add them together. So first, let's find the derivative in respects to our input of a of 1/3 times 3 to the a. Well, we can see that we have a multiplier of 1/3, so that constant, we know that constant rule, will just come out. And then we'd have to take the derivative of what's left. So 3 to the a, that is an exponential function because our variable is the exponent. So to find the derivative of 3 to the a, that's the natural log of the base times 3 to the a, which you could simplify to just the natural log of 3 times 3 to the a all over 3. So that is the derivative of the first part. So we're going to take that, whatever that may be, and we're going to add it to something else. So I'm going to take that and just get it down here in my answer. Now the second part that we'd have to do would be to find the derivative of that second term, and that second term that we wrote here would be this. Now if we thought about the derivative of that one, we're trying to confuse you with the e there, but we're trying to find the derivative in respects to a of a to the negative 1/2 times e. Now in this case, e is totally just a multiplier. There's no variable on it, there's nothing on it, so it just becomes our constant. So e times whatever the derivative of what's left would be. Now this is just totally a power rule, so we'd take that power of negative 1/2, slide it in front as a multiplier. So negative 1/2. And then the original base and the exponent would be subtracted by 1. So negative 1/2 minus 1 is negative 3/2. So you might want to clear that up, or clean it up, I would say. So on top we'd have negative 1 times e, and on the bottom we'd have 2, and then the cubed root of a squared. Just go ahead and again reminding ourselves that the negative exponent sends it to the bottom. Top one is the power, bottom one is the root. So that's the second half of our sum. So I take that again, which was terrible, we'll take that. And that's what we would then add to the derivative of the first term, because originally they were being added together. So then this would be our final answer. So here's number 8. I ran out of room on the last slide, so I'm just going to kind of apply it here. I'm just going to kind of show my work in a little different manner, a little bigger, in case you've been feeling a little stuck. But we can see that our function g is really just a difference of a bunch of different functions, or the sum and difference. So we can just apply the sum and the difference rule. So we're going to kind of take each term separately and find its derivative. So here, we could find the derivative in respects to x, because that's the variable we see at the exponent. Now here, it looks like our base is pi and our variable is an exponent. So that means the derivative will be the natural log of the base times the original function. So we have found our derivative of pi to the x is just the natural log of pi times pi to the x. Now we're going to have to subtract something. So I'm going to go ahead and just put a big old minus sign and then some parentheses, because we don't know what we're subtracting yet. We want to keep track of our signs. So the minus sign has already been transferred, so we're really just looking for the derivative in respects to x of 1/3 x to the power of e. Now the big thing here that we want to note is that we can see that the 1/3 is just a constant. This will be a constant multiplier of our derivative. But after we pull that constant out, all we see here is x to the e. We have to notice there is that our variable x is the base, not the exponent. So this is not an exponential function, this is our power rule. So we take the exponent and slide it in front, e, and we take the base and reduce the original power by 1. Then finally, we have our last term here, so we're going to add something. So we're going to add whatever the derivative of this is. Now it's important to see that that's just the square root of 2 times e to the x. So if we were looking for the derivative of the square root of 2 times e to the x, square root of 2 is just a constant. So as we've seen before, that constant will come out. After we pull that constant out, what is the derivative of e to the x? Well, that's just itself. So we might, maybe want to simplify it a little bit, write it a little nicer, but we have the natural log of pi times pi to the x. And then here, I'm going to rewrite that as 1 fraction. So we have a minus, and then 1/3 times e times x to the e minus 1. Just be rewritten like that. And then over here, we'd add the square root of 2 times e to the x minus 1. Last example I've included here. Certain pieces of antique furniture increased rapidly in price between the 70s and 80s, and they give us a function that describes the value in dollars in relations to time. So part A, we're supposed to find a formula for the rate in dollars per year at which the price is increasing. You see the word rate right there. We're looking for the rate at which the price, which is V, is increasing. So we're looking for the rate in which V would be changing. So we're looking for the change in the dollars in respect to time. That's the definition of our derivative. So in other words, they want us to apply the derivative rule. So the derivative of our function, we can see that our function is simply a exponential function. There's a constant multiplier of 75. So that constant multiplier, of course, will stay as a constant multiplier. And then the derivative of what's left after that constant multiplier, just some number raised to an exponent, is our exponential rule. So the natural log of the base times the original function. And I ran out of room, so I'm just going to write it below. So our derivative, v prime, would equal 75 times the natural log of 1.35 times the original function, which is 1.35 to the t. Now part B just wants us to use that derivative rule to find what the v prime of 5 would really mean. So they're asking us to plug in 5 into our derivative formula. So you should go do that. And we'll see that it approximately comes out to what, like 100 or something like that, 100.92 somewhere. And I'm just going to round arbitrarily to the second decimal place. So 100.93. So that's what that means. So we've got to work on our labels here. So again, our original function gave us like a value. So this gave us value in dollars. So then if we looked at the derivative of that in respects to time, so it'd be the change in value according to the change in time, which in this case is years. So v prime of 5 is approximating that the value in 5 years since 1975 is 1980 is increasing by about $100.93 a year.